Okay, we shall move further. So in the previous class, we saw about backface algorithm, right? So basically, we were discussing about to decide whether an face is backface or a front face, fine, right? So why we are supposed to do this differentiation on front face and back face? This is mainly because, right? So whenever we render the information from the frame buffer to the output device, fine. Anyway, whenever it is a 3D object, the back faces are not visible for us. So what the researchers thought was, right, we shall not render the information of the back face to the output device at all. Right? It's just a waste of time and waste of space. So if we need to render only the information of the front face to the output device for displaying, so we need to decide whether a particular face is a front face or a back face for my computer. We need some algorithm. Okay, right? So that was the reason why we started with finding different types of algorithm. And this coming to this the second algorithm, right, which we name it as Z buffer algorithm. Okay, which we name it as Z buffer algorithm. Okay, fine, right? So Z buffer algorithm, fine, Z buffer algorithm. Basically, this algorithm uses image space approach for detecting visible surface. Visible surface means front face. Okay, fine. So, what is this image space approach? We have clearly seen the differentiations of classification of these algorithms, right? Object space approach and image space approach. In object space approach, it was taking a part of the object, that is edges or point, anything, right? And it was determining whether that belongs to front face or back face. But coming to the second type of approach, which we call it as image space approach, it takes pixel by pixel and it checks whether that pixel belongs to front face or that pixel belongs to back face. Okay, fine. And one of the disadvantages of that object space approach was, fine, it was not processing any overlapped object. Okay, fine. Overlapped object means, right, if one object was behind the other object, right, it was not processing that. All the objects should be independent to process a front face and back face of that object. That particular disadvantage was overcome by this Z buffer algorithm, okay, which we call it as image method in image space approach. Okay, fine. So where the Z buffer algorithm also considered, or it was also successful in differentiating the front face or the back face, that is the visible surface, fine, whenever there is a overlapped objects also, fine, right? See here, this is a overlapped object. See here are I can find three objects, right? So actually how this will be placed, right? This object, fine, right, this object will be placed below this object and this object is placed below this object. So for the clarity of explanation, right, I have spreaded this object like this, right? How actually these three objects are is, right, it is one upon the other. Okay, on top we have this object, below we have this object, and below that we have this object. Fine. Whenever we have overlapped objects, right? So which object will be visible? Obviously, the object which is on the top. Okay, that will be visible. Which is overlapped, that object will not be visible for us. Right? That is the common sense that we have. So we shall prove that by algorithm. How I will feed the algorithm to the computer to detect the face, right, which is upper and the face which is at below, right? So that the below faces will not be visible for me, and it considers only the upper faces as visible faces. Fine, right? So this algorithm, the aim of this algorithm is that, right, whenever we have overlapped object, fine, how this algorithm detects the visible surfaces and invisible surfaces. Fine. So it uses depth buffer method, which compares the surface depth throughout the scene for each pixel position on the projection Fine. So that means what technology is used here is, right, we based on the z-axis value of my object. Based on the z-axis value of my object, in the sense, right, whenever we have a 3D object, how do we determine x-axis, y-axis, and z-axis? Right? X-axis says the length, y-axis says the height, and z-axis says the depth. Okay, right? So that means based on the depth of the object, okay, right, based on the size of depth of the object, we will be determining the front, which object is in the front and which object is at the behind. Okay, how we will do that? That is what this algorithm tells me. Based on, right, what is the key technology here is used? It is the value of z axis. Z axis means depth. Okay, fine. So that is how the name came for this, as Z buffer algorithm. Fine, right? So now let us see here. Okay, how does this work? Fine, right? So before that, I will tell you what is the measurement of Z. Okay, right? So the measurement of Z is the distance between the projection plane and the object. This is the projection plane. Okay, right? See, for example, you people may be seeing. Okay, right? So you people may be watching this video. What is the depth of this? What is the depth value is? Fine, right? It is the distance between your eye, okay, right, and the monitor. Okay, that is the Z value, right? That means it is the distance from the projection plane to my object. Okay, this is the distance from projection plane to the first object. What is the distance? 2 units. Okay, right? So now what is the, that means the Z value is 2 for this object. Fine. Now what is the distance from the projection plane to the second object? It is 4 units. Okay, on the same lines, what is the distance of the, that is what is the value of Z for the third object? It is nothing but it is the distance from the projection plane to that object. Okay, that is 8. Fine. So this is about the prerequisites of this algorithm. Okay, so this algorithm basically works considering pixel by pixel. Okay, fine. That is the first prerequisite. And second prerequisite is, right, this algorithm works on the z-axis of the object. That is the length of z-axis of the object. So the third one is, what do you mean by that z-axis? Okay, the meaning of z-axis is nothing but the distance from the projection plane to that object. Okay, so for the first object it is 2 units. On the same line, second object it is 4 units, and for the third object it is 8 units. Fine. So now let us check the working of this. Okay, right. So now for the implementation of this Z buffer algorithm, okay, right. So we will be requiring 2 buffers. Okay, we require 2 buffers. Okay, right. So those 2 buffers are called as depth buffer and frame buffer. Okay, right. So where this horizontal, this row says y values and this column says x values. Is this clear, right? For both of the buffers, right? So our column says, row says x values and column says y values. Okay, right. So first one is initialization. Okay, so initialize the depth buffer and the frame buffer so that all the buffer positions x, y. Okay, right. So first what I will do is, right, I will initialize all the this is the z values we will be storing, right, for respective x and y, right. What is the z value? Fine, right. So we will store all these z values first with 1. Okay, right. So I will store this. Sorry. Okay, fine. So what are all the things that I will be doing, right? So I'll be storing this all the table, that is all the boxes with 1. Okay, in the depth of initialization, right? And what I will be storing here is, right, I will be storing in the frame buffer for each x and y, that is x is columns and y is rows. For each of these cells, right, I will be storing the background color at that particular position. Okay, the background color is black, white, or what is that, right? That I will be storing it here. Fine. So next, fine. So I will process each polygon in the scene at a time. Okay, as follows. Fine. Okay, right. So now come to this, right? For each projected XY pixel position on the polygon, we calculate the depth Z. Okay, if not already, no. If the Z is less than the depth buffer, okay, we will compute the surface color at that position and we will set the depth buffer of XY is equal to Z and frame buffer of XY or surface color is equal to, that is the surface color is equal to surface color of XY. So let us come to the previous slide to understand this. Okay, right, for each projected XY. Okay, right. So now come to this, right? So now let us these things, right? What I have taken 2, 4, 8, right? Units. These are -2, -4, -8. Okay, right? It is not +2, +4, +8. It is -2, -4, -8. Okay, right? Why it is -2, -4, -8? I will tell you now, right? See, this is the viewing perspective. Okay, right? Where this is X, where this is Y, and where this is Z. Okay, right? So this is Z means it is positive Z. Fine. So now if this is Z means, right? So where I am looking, where is my eye looking at, right? It is looking from plus Z to minus Z. Correct. Up to here it is plus Z. After that this is minus Z. Complete. Right. So as this is minus Z, so I call these, I will say these as -2, this as -4, and this as -8. Not +2, +4, +8. It is just for understanding I had written, right? Now I'm coming to the correct signs of this, right? As I'm looking from positive Z to negative Z, right? So this is positive Z, obviously this is negative Z. Okay, right? So this becomes -2, this becomes -4, and this becomes -8. Fine, right? So now, what this says, right? This says, right? It will be checking the pixel position, all the pixel position. Okay, fine. So now come to this pixel. Okay, right? So now when you come to this particular pixel, I say this particular pixel position is 2, 1, 2. That is X is 2, Y is 1, and Z is 2. That is -2. Okay, right? This is 2 units, right? So as I'm looking from positive Z to negative Z, right? So this becomes -2. So hence this is -2. Okay, fine, right? So now what the algorithm tells is, okay, right? So this is -2, this is -4, this is -8. Okay, fine, right? So now what my algorithm tells is X is 2, Y is 1, and Z is -2. Remember this, X is 2, Y is 1, Z is -2. Now come to this, right? I'm checking for each projected XY. What is XY, right? So X is 2, Y is 1. That is X is 1, 2, here 2. Y is 1 means this, right? I'm talking about this cell. Okay, this is where, right, I need to place the Z value of that particular XY. That is 2, 1. Okay. So now, what will be initialized with, first with all these things, right? All these things will be initialized with 1. Okay, right? So now I am at that particular position X, Y, Z, right? Where my X is 2, Y is 1, and Z is -2, right? So what is Z value? Z value is -2. Okay, right? Now I will check this condition. If Z is less than depth buffer of XY, what was depth buffer of XY here? It is 1, right? Because I have initialized everything to 1, right? So yes, if Z is less than depth buffer of XY, yes, my Z is -2 and depth buffer is of XY at this particular position is 1 because everything is initialized with 1. Yes, it is less. So what I will do, I will replace this depth buffer with Z. Okay, that means at this position where it was 1, 1, 1, right, I will replace that with -2. Okay, right? and I will compute the surface color at that position, right? What is the color of that position, right? So here it was a background color, right? Some background color black or something white was there. Fine. So here I will substitute the what is the color at this particular pixel position to this place. Fine, right? So this is the algorithm process that I will be doing. Okay, right? So next I will take the next z value, right? And I will go on computing. Okay, right? To determine that is back faces. Fine, right? So it's obviously here we will determine, we will be in this algorithm will be determining front face. Okay, right? So what was the next coming to this previous slide? Yes, coming to this slide, right? What is the next value? Next value is 4 and next value is 8. Okay, when I take 4, right? So 4 is less than, sorry, right? 4 is less than 2? No, right? So minus 2 will be there only, right? On the same lines, I will next consider 8 as that value at that particular position, right? So 8 is less than 2? No, 8 is also not less than 2. So minus 2 will be here. Okay, right? So minus 2 is here. On the same lines, it will start calculating the z values at each and every particular pixel position. If I take any pixel position, right, that corresponding pixel position of for this plane, that corresponding pixel position for this plane, and that corresponding pixel position for this plane, right? So I will compare the z values, and whatever the less z value is there, right? Obviously, it is 2, 4, 8, right? The less z value is 2. That means, right, this particular face is on the top. That is this is first. This is on the front, right? On behind this plane, I have this plane. Behind this plane, I have this plane. It is a common sense, right? So what happens, right? So like this, I will be calculating for each pixel position on the scan lines, right? Each, if I take a pixel position, right, the corresponding pixel position on the on the second object, and the corresponding pixel position on third object, right? XY remains the same for these things, right? Only things that differs is Z value. Okay, for this point, right, 2, 1 and Z value becomes 4. For this, right, it is 2, 1 and Z value becomes 8. Right? So I will go on comparing the Z values, right? So whichever Z value is less, right, that Z value I will be placing on my depth buffer. Okay, right? Now, after all the surfaces has been processed, the depth buffer contains the depth values of the visible surfaces, right? Front faces. So what this contains, right? This contains the Z values of all the front faces. Because I'm comparing less than, I'm comparing this less, right? Obviously, fine. My the nearest planes Z value will be less than the farthest plane Z values, and so the nearest plane means the first object, that is the front face of the first object which needs to be displayed. Those Z values will be present, and I consider those position X, Y, and Z. Okay, right, along with the colors, right? I consider those pixels or those points as the front face, and I will give only those front faces to render it to the output device, right? And all other pixels, right, that is the overlapped object pixels will be completely eliminated. Okay, fine. So now my question is, right, whenever I start going with the object, right? So, okay, first I will find this pixel, next I will find this pixel, next I will go on finding the pixel value, pixel values of each of this pixel, right? So now, should I, what is the procedure for that? First I will find this pixel, next pixel. What is the formula to find the Z value? Okay, right? So that we have a simple uh, how to find the z values at each pixel, right? Each pixel that is represented by xy. Fine. So we know that, right? Right, any plane is represented by ax plus by plus cz plus d is equal to 0. We saw this in backface algorithm. Okay, right, where x, y, z are pixel position for a point, right? So now how do you calculate z? Ax plus by plus cz plus d is equal to 0 means what is z value? It is minus ax plus by plus d plus c. Fine, right? So now, yes, use z value I calculated like this for the first pixel. So next, this is the pixel thing. So for the next pixel, I need to calculate the z value. Okay, right? How do I calculate the z value? For the next pixel means, right? So x will be incremented by 1 and y remains the same, right? So what is xz? Xz means next value. Next value is nothing but, right, x will be incremented by 1. Okay, because from here I am moving to the next pixel means x is incrementing, not y, right? So x is equal to x plus 1 and y remains the same thing. So z dash is equal to minus a of x plus 1. Instead of x, right, I will replace this with x plus 1. So finally, what happens for x plus 1 comma y? My z dash is a of x plus 1 plus minus a of x plus 1 minus by minus d divided by c. That means minus ax plus c minus a by c minus by c minus d by c. Okay. Now, if you consider all this red colored one, that is minus ax minus by, okay, minus d whole divided by c, that is nothing but z. So I can replace this z dash is equal to z minus a by c. So how to get the next pixel's z value? Okay, right? So it is simple. If you just subtract the previous z value, right, with a by c constant. Okay, I will get the next pixel's z value. That is what they say. Okay, right? So where the ratio minus a by c is a constant for each surface, right? So this minus a by c, what I got is a constant for each surface. Fine, right? So succeeding depth values across a scan line are obtained from preceding values with a single addition. That's it, right? So if it is nothing, what is right? So it's nothing but z minus a by c to the previous z. If I do minus a by c, I will get the next z value. Okay, we can implement the depth buffer algorithm by starting at the top vertex of the polygon, right? And then we will recursively calculate the z coordinate values from left edge of the polygon. That means, right, I will start from top, right, and for each of the scan line and for each of the pixel, I will go on finding the z values, right, and I will be checking the z value which is of minimum, right, and I will replace that with, and I will replace that in the depth buffer. Okay, right, like this I will from the left to top edge I will go on doing for each of the scan lines. First next I will come to the next scan line, next. This is how I will go on moving, and I will go on finding the that is depth values for each of the surfaces. Okay, right. Now how do you find x dash? From x to x dash, it is nothing but x minus 1 divided by m. Okay, x dash is what we thought, x plus 1. Always it will not be x plus 1, right? So in general, how do we calculate x dash is equal to x minus 1 divided by m. Okay, right? So this is how I calculate the depth buffers, and based on the depth buffer, I will select which is the front face, right? See here, that is fine. If I take this example, what is the depth value of this? If I take this pixel, right, this pixel on this surface, this same pixel on this surface, and this pixel on the same surface, right? So I need to check whether this pixel is front face, this pixel is front face, or this pixel is front face. So I will check this z values. Z value means, right, which is nearer to my plane. Okay, so the value, so this is 2 units, and this is 4 units, and this is 8 units. So for each of the surface, right, I will compare the z values, right? So wherever z becomes less, fine, that z value I will add to my frame buffer. That for each xy I will add that value to the frame buffer, and those pixel positions, right, x, y, and the z values will be the front faces. That is what they do, right? So we'll be having depth buffer, right? I will, for each of the pixel position, right, I will check z and I will compare with depth buffer. Here 2 will be there starting. Next I will get 4. I will check 4 is less than depth buffer. No. So 2 will be here only. Next I will get 8. 8 is less than 2. No. So here 2 will be there. So 2, 1, 2. This pixel, right, is the front face. Like this, I will go on finding the z values for all the pixels for each of the surfaces, right? And whichever pixel z value is lesser, I will treat that as front face, and I will remove all other pixels before I render it to the output display. That is how I will detect the front face using z buffer algorithm. Okay.